Let's review the summary of equations in our toolbox for Chapter 6, which were thermodynamic problems involving the calculation of entropy. Let's review the equations in our entropy toolbox. We know that for a reversible process, no entropy is produced. So we can write that the change in entropy of a system during a process plus the change in entropy of its surroundings must equal 0. So sometimes the change in entropy of a system can be decreased, but the change in entropy of the surroundings would be increased by an equal amount, and so the sum would be 0. Now, if we have an irreversible process, we know that entropy will be produced. And in that case, the change in entropy of the system plus the change in entropy of the surroundings is greater than 0. Now, it would be possible for delta S for the system to be less than 0, but in that case, delta S for the surroundings would be a greater number so that the sum would be greater than 0, because in irreversible processes, entropy is always produced. Now, it goes without saying that if I evaluated a potential process and I got that the delta S for the system plus delta S for the surroundings was less than 0, then I know that that is an impossible process. We introduce the TdS equation, which simply says that the heat transfer for an internally reversible process is the integral from state 1 to state 2 of TdS. Now, for constant temperature, this simplifies to the heat transfer of an internally reversible process is just the temperature times delta S, which we can write as the mass times the change in specific entropy. We also developed a entropy balance for a closed system, and in words, it's fairly straightforward. It says that the entropy change within the system during a process is equal to the net entropy transferred into the system by heat transfer, plus the amount of entropy produced within the system by irreversibilities. So in equation form, we can say that the entropy change is S2 minus S1. The entropy transferred into the system by heat transfer is the integral from state 1 to state 2 of dq over T evaluated at every boundary, plus the entropy production. Now, if we have a constant temperature, we can simplify that. It's the change in entropy during a process, S2 minus S1, is the summation of Q over T evaluated at every boundary, plus the entropy production. Now, because entropy production is generally the term that we're looking for, let's rearrange this equation and solve for sigma. It's simply S2 minus S1, which we can write as the mass times the change in specific entropy minus the summation of Q over T evaluated at every boundary. Now, we can also write an entropy balance as a rate balance. So in a rate balance, of course, entropy and heat transfer are all divided by time. So we have that ds dt is the integral, or excuse me, it's the sum of q dot over t evaluated at every location j where heat transfer takes place, plus the rate of entropy production. Now, in steady state cycles, ds dt is always 0. And we can write then that the negative of the rate of entropy production is the summation of q dot over t evaluated at every location j where heat transfer takes place. Now we can do something similar for an open system entropy balance. And remember, open systems we evaluate as being steady state and having one inlet and one exit for flow. So we can write then that sigma dot, which is the rate of entropy production, is the mass flow rate times the change in specific entropy minus the sum of q dot over t evaluated at every location j where heat transfer occurs. And we can divide this entire equation by the mass flow rate, and we can solve for the rate of entropy production per unit mass of flow rate. And that's just the change in specific entropy minus the summation of Q dot over M dot divided by T, evaluated or summed at every location J where heat transfer takes place. Now, this was a very important equation. When we're dealing with incompressible fluids and solids with constant specific heats, we have a different way of evaluating the entropy change during the process. The change in specific entropy, S2 minus S1, for solids and incompressible liquids is just the specific heat times the natural log of T2 over T1. We have particular ways of dealing with ideal gases. With ideal gases, we can write that the change in specific entropy is the integral between T1 and T2 of C sub V over T dt plus R natural log of V2 over V1. Now, we can certainly evaluate this second term, but this first term is very difficult to evaluate since C sub V is a very complex function of temperature. So it has been tabularized for us. This integral can be replaced by this term, S naught of T2 minus S naught of T1, where these S naught values can be found in tables of ideal gases. So this original expression simply becomes that the change in specific entropy is S naught of T2 minus S naught of T1 plus R natural log of V2 over V1. Well, we have a second expression for these, excuse me, we have a second expression for the change in entropy for an ideal gas process. It's the same integral, but instead of plus R natural log V2 over V1, we have minus R natural log of P2 over P1. Well, we're going to deal with this first term the same way. It's going to be S naught of T2 minus S naught of T1, where these S naught values are taken from a table. And then we simply have minus R natural log of P2 over P1. Now, when we're dealing with ideal gas processes that have constant specific heats, then the first term of this equation can be evaluated without resorting to tables. We can evaluate constant specific heats. So we have S2 minus S1 is C sub V times the natural log of T2 over T1 plus R natural log of V2 over V1. Or in the second case, we can write that S2 minus S1 is C sub P natural log of T2 over T1 minus R natural log of P2 over P1. So we have multiple ways of evaluating the entropy change of processes involving ideal gases. Now, in a particular case where we have an ideal gas taking place in an isentropic process, we have this relationship. P2 divided by P1 is simply the exponential function of S naught of T2 minus S naught of T1 divided by the gas constant. And we can find these S naught values for various common gases in tables. We also developed multiple equations for very specific combinations of processes. So here we have an ideal gas undergoing an isentropic process with constant specific heats. And in that case, we have numerous relationships relating temperature and pressure and volume using K, which is the ratio of specific heats, C sub P over C sub V. I'm not going to read all of these, but you can see in this particular set of circumstances, we have numerous relationships that will help us evaluate the results of a process. And recall that for Constant specific heats, K is the ratio of specific heats, C sub P over C sub V. C sub P is Kr over K minus 1, and C sub V may be evaluated as R over K minus 1. Now, for air only and no other gas, if we have air involved in an isentropic process, we have table values of P sub R and V sub R. And we can write that P2 is to P1 as PR2 is to PR1. And V2 is to V1 as VR2 is to VR1. We also looked at the performance of turbines, nozzles, compressors, and pumps. And we wanted to calculate their efficiency where we're comparing their efficiency to that of an isentropic process. Now remember, an isentropic process is reversible, so it produces no entropy. It has no heat transfer, and the change in entropy during the process is 0. So for an isentropic turbine, the efficiency is given as the work output of the turbine divided by the mass flow rate over the work output of a turbine undergoing an isentropic process divided by its mass flow rate. And this can be evaluated as H1 minus H2 over H1 minus H2S, where H2S is the enthalpy at state 2 of the isentropic process. Now, if we want to evaluate the efficiency of an isentropic nozzle, that efficiency is just the velocity at the exit squared over 2, divided by the velocity at the exit of an isentropic process squared, divided by 2. If we're evaluating the efficiency of compressors and pumps, the efficiency is the power input required by the compressor or pump divided by its mass flow rate, that taken for the isentropic process, divided by the power requirement of the compressor or pump divided by its mass flow rate. And this is reduced to H2S minus H1 over H2 minus H1.